In this video, we'll look at VSPER theory and the polarity and dipole moments of molecules. When we look at our molecules, we want to look at its bond polarity, bond angle, and its dipole moment. So if we take all these together, we can figure out if we have a polar molecule or a nonpolar molecule. So now let's go through these concepts and look at carbon dioxide as a first example. If I remember carbon dioxide, and I draw its Lewis structure, it'd be an oxygen bonded to a carbon that's double bonded to another oxygen. And each oxygen has two lone pairs on it. Now, if we were to look at the electronegativity difference between a carbon and an oxygen, and I look at that bond, the carbon has an electronegativity of 2.5 and oxygen was 3.5. So we know already that is a polar covalent bond with the dipole pointing from the carbon to the oxygen. And we also know carbon dioxide is a linear molecule because there's two electron domains on there. There's two electron groups on there. And so that means we end up with one dipole pointing from the carbon to the oxygen and a second dipole pointing from the carbon to the second oxygen. Those two dipoles are pointing opposite of each other. They're 180 degrees apart. Since they're pointing opposite, their polarities will actually cancel out. This means that overall, carbon dioxide has no net dipole moment. So carbon dioxide would actually be considered a nonpolar molecule. Even though it has polar bonds between carbon and oxygen, the two dipoles cancel each other out, giving me a nonpolar molecule overall. When we're figuring out a polarity of our molecules, it's fairly easy to figure it out when it's a linear molecule like this. What about when it's not linear? Let's look at another example with water. So water, as we see from its Lewis structure here, is an oxygen bonded to two hydrogens, and it has two lone pair domains. So it has two non-bonding and two bonding, which gives us a bent shape. And then if we also look at the bond between oxygen and hydrogen, oxygen's electronegativity was 3.5 and hydrogen was 2.1. Again, we have a dipole pointing from the hydrogen towards the oxygen. So we have a polar bond between these two atoms. But now we want to figure out if the overall molecule is polar. If I look at the dipole for hydrogen, between hydrogen and oxygen here, both bond dipoles are pointing up towards the oxygen. Since they're both pointing in the same direction, they're going to add to each other. It's going to be an additive effect. So that means the overall dipole for water actually points up and points towards where those lone pairs are. Since there's nothing to cancel out the dipoles here pointing up, plus we have lone pairs, overall, water would be considered polar, and the dipole points upwards straight up from the oxygen. And so we can see with our two examples here, carbon dioxide, the two dipoles canceled out, so it was nonpolar overall. Oxygen, the dipoles don't cancel out, so it's a polar molecule. And we can do this for any molecule we have. So if we look at other molecules, example, if we have carbon tetrachloride or chloroform. Carbon tetrachloride here, I have a chlorine, I have a carbon and each chlorine on it. You can see that we have dipoles pointing in each direction. The carbon-chlorine bond is a polar bond. But since all four atoms connected to our central one are the same, all the dipoles will cancel each other out. So that's one key idea. If the dipoles are the same, that's one key idea. If all the atoms connected to your central one are the same, no matter how polar the bond is, all the dipoles will cancel each other out. If, however, there's a different atom thrown in, like hydrogen here, now it changes the polarity. So now the dipoles for the chlorines are all pointing downward. Between the carbon-chlorine bond, you can see they're all pointing downward. That means this molecule will will have an overall polarity. It has an overall dipole moment, which points straight down. So that means here we have our nonpolar molecule, and here we have our polar molecule. And the only difference we made was we switched a chlorine for a hydrogen. We can even see how this polarity would affect other molecules. So if we look at C2H2Cl2, they have what we call cis and trans isomers. We call it cis because the chlorines are on the same side. And then this one is trans because the chlorines are opposite to each other. So the chlorines we can think are transverse. And so what happens is if we have the chlorines on the same side here, like our first structure, they both have the carbon-chlorine bond has a dipole that points down towards the chlorines. So since it's pointing down towards the chlorines, overall, our dipole points downward. If we look at the trans, the two dipoles are pointing in the opposite direction. So they'll actually cancel each other out. So here our dipoles cancel each other out. Since they cancel each other out, the trans is nonpolar. So a cis configuration here happens to be polar, and our trans happens to be nonpolar. And having those different configurations actually leads to different physical properties. So our cis isomer is polar, our trans is not. The cis isomer boils at 13 degrees Celsius higher than the trans isomer. So it actually has different physical properties. You can separate the cis and trans here. And all we did was switch which side the chlorine was on, whether they're on the same side or opposite. And so you guys should be able to start figuring out if your overall molecules are polar or not by drawing the three-dimensional shape and then determining the dipoles of each bond. If the dipoles don't all cancel out, you know it has to be polar. If the dipoles do cancel out, you know it has to be nonpolar.